SwayamPrabha. Digital India. Educated India.
Today what we are going to do, we will study fluid dynamics inside human eye. So, like blood flows in our veins and arteries and it maintains some pressure, that is called as blood pressure. In the similar way, there is one fluid which flows continuously in our eye and that fluid is called as aqueous humour, and that fluid also maintains pressure inside our eye and that pressure is called as intraocular pressure. So, today we are going to study aqueous humour dynamics in human eye, or let us say it in anterior chamber of human eye. So, everything will be clear, like what is aqueous humour, what is anterior chamber and all in few minutes. So, as I said, like blood flows in veins and arteries, it maintains pressure. In the similar way, aqueous humour flows inside anterior chamber of our eye and that also maintains pressure, that is called as intraocular pressure. The other thing is, this aqueous humour functions in the same way as blood does for the other parts of body. Like what is the function of blood? It will provide nutrients and oxygenates different tissues and cells in our body. In the similar way, this aqueous humour provides nutrients and oxygenates different ocular parts in our body. So, the reason is blood cannot flow inside our eye because this is opaque material. So, if the light will enter inside, it will not allow it to go inside and fall on retina. So, that is why nature has provided us a transparent fluid inside our eye, so that when light enters it can directly go to pass over the lens and it can fall on retina. So, that is one thing. So, that is why colorless and transparent fluid which is called as this aqueous humour is present inside our eye. So, and it also oxygenates and provides nutrition to the ocular parts. So, this aqueous humour is transparent fluid and it provides, it oxygenates ocular parts. So, its functions are same as blood, but the thing is it does for the eye, whereas blood does for the other part of the body. Now, the another thing is anterior chamber. So, that is also new for all of you. So, I will draw it here, I will draw the full shape of our eye. So, our eye is spherical in shape. So, let me draw a sphere. So, it is something like this, and in the front part of our eye there is one bulged part. So, you can see that black part, that is bulged out part. So, this bulged out part is called as cornea, whereas this part is completely spherical in shape. Behind the cornea, the black part which appears as black part, there is another organ which is called as iris. So, this is iris and iris is black in shape, because of that this one small part appears as black, whereas the front part is completely transparent. So, this is iris, and there is a small gap between iris, and this is called as pupil. This is a small gap. And what is the function of pupil? It adjusts its size depending on the amount of light entering in our eye. So, suppose you go to a outside, you will see that your eye will try to contract. So, this actually the pupil contracts and it will allow less amount of light to enter inside our eye. Whereas, if you will go into a dark room, you will see that your eye will open up. So, actually the pupil opens up and it allows more amount of light to go inside. So, this pupil is a very small aperture which changes its size depending on the amount of light entering into the eye. And behind this iris there is another organ which is called as lens. So, this is lens, and this part is called, so behind the lens there is region, this region is called as posterior chamber of our eye, or let us say it posterior chamber. And near this back end of the posterior chamber we have retina and optic nerves. So, this optic nerves transfers the signal to the brain, so that we can understand what we are seeing. So, that is the work of optic nerve, and this retina is for formation of image there. And the region between iris and cornea, that is called as anterior chamber. So, this region is called as anterior chamber. Okay. So, what I mean is this aqueous humour flows inside this anterior chamber. So, there is a chamber, the front part is slightly curved and there is iris from this side. So, this is the region in which aqueous humour flows continuously. So, in this region aqueous humour is present. So, today we are focused to find how this aqueous humour is flowing inside the anterior chamber. And one thing which I want to make clear today, that this aqueous humour is different from the tear. So, when we cry the tears comes out. So, that is different from aqueous humour. This aqueous humour is completely inside the cornea, whereas tear film is over the cornea. So, if this is cornea, so tear film is on this surface, whereas aqueous humour will be in this surface, like inside the cornea. So, this tear film is different from this aqueous humour. So, our focus today is on modeling the dynamics of aqueous humour inside the anterior chamber. That is what we want to do today. So, let me give you some importance of this work, why this work is important. So, when we talk about blood, we talk about blood pressure. So, you will see that many people go to doctors regularly for blood pressure checkup. So, blood pressure is measurement of how healthy we are. So, in the similar way, the pressure inside our eye is measurement of how healthy our eyes are. So, when you go to a doctor, they will check your eye pressure and they will see whether your eye pressure is within the normal range or not. So, eye pressure is measurement of measure of health of our eye. And it is aqueous humour which contributes to the intraocular pressure in the eye, and it is aqueous humour which contributes to intraocular pressure. So, when we are saying pressure of the eye, that is called as intraocular pressure. So, I will use IOP for intraocular pressure. The second importance is, so what I mean from here is that if the flow inside the anterior chamber is controlled or in normal way, the intraocular pressure will remain in the normal range, whereas if there will be some like deviation from the normal behavior, then the intraocular pressure may increase or decrease. And if that pressure will be not in the normal range, there is one eye condition which is called as glaucoma, you would have heard it. So, glaucoma is an eye disease in which the pressure of your eye will not be in the normal range, it will deviate from the normal range. So, intraocular pressure will deviate from normal range, and this deviation causes damage to the optic nerves. So, optic nerves are the nerves which transport signal to the brain, whatever we are seeing, that signal will be transported to the brain, and then we will be able to understand what we are seeing. So, if the pressure in this chamber increases, what it does, it will press all the organs towards the back, and that will cause the collapse of the optic nerves, because optic nerves are there in this on these walls. So, because of this high pressure, this optic nerves will be collapsed. So, the blood will not flow through these nerves, and because of that the nerves will die. So, this pressure should be always in the normal range for the proper functioning of eye. And once if these optic nerves are damaged, they cannot be regained back. That is the another thing, that once it dies, it cannot be regained back, even with the surgery you cannot regain it back. So, it will lead to permanent blindness, and in India and in other countries also, many people are have this type of syndrome, like they become till 40 years they will be completely fine, and after some time they will be complete blind, and unfortunately nothing can be done in this case, because optic nerves are damaged and they cannot be regained back even after surgery. So, this study is important to understand how glaucoma proceeds, like how pressure is generated or becoming more in this chamber because of fluid dynamics, and how it is damaging the optic nerves. So, this study is important with that point of view also. The other thing is drug delivery. This is also important if we talk about drug delivery inside eye. So, what I mean is, this aqueous humor is completely continuously flowing inside. So, if we put any drop of drug over our eye, so I am talking about some drug solutions which we put on our eye, or any ointment which we apply over our eye. So, that drug diffuses inside from this cornea. So, this cornea is a solid material. So, from this cornea, if we put any drug here, this will spread over this cornea and this will diffuse inside on the inner wall of cornea. From there, because aqueous humor is continuously circulating inside this chamber, so this drug will be taken by the aqueous humor and it will spread all over the eye. So, what I am talking is, suppose this is, I am now drawing only the anterior chamber of our eye. So, this is anterior chamber of our eye, and I am saying that aqueous humor is continuously circulating inside. So, let me draw a simple schematic like this. This is aqueous humor and it is continuously circulating inside. So, this will be somewhere here also, it will be circulating like this. So, if we put a drop of drug here, it will spread all over the cornea and then it will diffuse inside. So, the drug particle will come on the inner wall of this cornea where this aqueous humor is moving. Now, this aqueous humor will take this drug with it and it will spread it all over the eye. So, can we control these flow patterns in such a way that we can transport the drug more effectively? That is the another question. So, can we control these flow patterns in anterior chamber for effective drug delivery? So, suppose I have infection somewhere here on the iris, can I control this flow pattern so that if drug is here, it can directly reach here? So, can this be possible? That is the another question. So, is there any way to control these patterns? So, these are the motivation for today class, that why this study is important. Okay? If you have any question, you can ask at this point. So, now what we will do? We will take the actual dimension of anterior chamber and we will try to model this fluid. We will understand what are the mechanism which drives this flow, and we will see how these flow patterns can be regulated. Okay? So, before that I want to explain one another thing. So, how this aqueous humour is coming into the anterior chamber of our eye. So, I want to explain you that thing. So, there is another organ which is called as ciliary body in eye. So, that will be somewhere near here and it is on the both side of the eye. So, that is called as ciliary body. So, let me write it here, this is ciliary body. So, this organ continuously produces aqueous humour. So, this is ciliary body and this will continuously produce aqueous humour in our eye. And what will happen? The produced aqueous humour will enter into the anterior chamber through a small gap between this iris and lens. So, this is iris and this is lens, through that a small gap it enters into the anterior chamber, and here it circulates and then it comes out through trabecular meshwork, which is another organ somewhere here. So, it can come like this or it can come like this. So, what I mean here, let me explain you from here in slightly more clearly. So, this is anterior chamber of our eye. So, aqueous humour will enter from here, which is pupil. So, it was produced somewhere here, from here it enters like this, and then it can go either like this, where this is trabecular meshwork, or it can go like this. Here also you have trabecular meshwork. I am writing that as TM, trabecular meshwork. Or if there is another mechanism, it can make it, make patterns inside the anterior chamber. So, what I mean to do here is, like if aqueous humour is produced continuously, it is continuously coming out also. So, this process is continuous. So, because of that, this continuous process, the total amount of aqueous humour inside the anterior chamber will remain constant over the time. So, what I am saying, that this is continuously produced at a constant rate, this is continuously exiting out from the anterior chamber at constant rate. So, the total amount of aqueous humour inside the anterior chamber will remain constant over the time. So, at t equal to 1, if some volume V volume of aqueous humour is there inside the anterior chamber, at t equal to 2 also V volume will remain, because this process is continuous. So, because of this, we can consider this anterior chamber as a closed volume. So, what I am saying, that the amount of aqueous humour inside the anterior chamber is constant over the time. So, that is why we can consider that the anterior chamber is a closed volume where the amount of aqueous humour will remain constant over the time. Okay. So, yeah, so this is closed volume of anterior chamber. Now, another thing which I want to make clear that the flow patterns inside the eye or inside the anterior chamber will depend on the position of the eye, position of a person. So, suppose I am standing, so I am seeing towards the front. So, our cornea is something like this, right. So, the bulged out part is facing towards horizontal, whereas if I will sleep, then I will face towards vertically up. So, the bulged out part or the curved part will be up. So, this is when a person is sleeping, let us say it to be 1, and the second case can be when a person will be standing. So, in that case the bulged out part will face towards the horizontal. So, this can be two case, simple case. So, this is the one when person is sleeping. So, in sleeping position the person will face vertically up. So, this curved part is vertically up, whereas in standing position the person will face towards the horizontal. So, this curved part is towards the horizontal. So, this is when person is standing. And you can see that the gravity will always act towards the down, whether we are standing or sleeping, it will be always the action of gravity will be always vertically down. So, in both the cases you can see that in this case the gravity is acting so, suppose this is the depth of the anterior chamber. So, here the gravity is acting in the direction of depth of the anterior chamber, whereas here in this case the gravity is acting in the direction of width of the anterior chamber. So, there is a small difference because of the orientation of the eye. So, the flow patterns will also change because of this, and we will see it after few minutes that how it will change. Okay. So, now let me give you the dimension of the eye. So, today what we will do, we will take only one case which is sleeping position, and in this case we will model the fluid dynamics inside eye. So, let me give you the dimension of the eye. So, suppose this is the center and this is the width of the anterior chamber. So, this width of the anterior chamber is 11 mm, whereas the depth of this anterior chamber is 2.75 mm. So, what we can see clearly here is the width of the anterior chamber is far greater than the depth. So, what it means that the dimension in one direction is very larger than the dimension in another direction. So, we can use lubrication approximation which we have studied earlier. So, because dimension in let me write it width of anterior chamber, I am writing anterior chamber as AC, is far greater than its height or depth, we can use lubrication approximation to model fluid dynamics. Okay. So, this is aligned with whatever we had studied earlier. In lubrication approximation, you would have seen that the dimension in one direction was far greater than dimension in another direction. Okay, so this is the width of the anterior chamber, which is 11 mm. This is the depth of the anterior chamber, which is 2.7 mm. So let us call this width as L and this depth as B. So I am saying that L is equal to 11, B is equal to 2.7 mm, and let us keep our, so to solve any problem, first we need to choose coordinate axis, right. So we are choosing Cartesian coordinate system and the origin is at the center here. So here this is x direction, this is let us say that z direction, and this is 0 0, and I am saying that this is completely at the center of this width of the anterior chamber. So this will be L by 2 0. So let me write it here, L by 2 comma 0, and this is minus L by 2 comma 0, right. So if you have understood till this point, so this is our model problem, where in this is anterior chamber, inside it aqueous humour is there and that is continuously flowing. So now the question is, when we talk about solving any flow problems, first we see what is the mechanism which drives the flow. So in some cases you have seen that pressure difference is there, that drives the flow. In some cases some shear is there, that drives the flow. So here what is the force which drives the flow inside the anterior chamber? So to explain that, what I will do, I will draw the schematic again here. So this is anterior chamber of our eye and this is iris and this is cornea. Okay. The thing is, so here there was a small gap which was pupil. So we have, because that is very small gap, so I have approximated that it is iris is continuously all over the width, because that gap is very small. So because of that we can approximate that it is completely iris surface only. Now the thing is, this iris contains blood vessels. So in iris blood vessels are there and blood flows continuously in those vessels, and because of that blood flow through these vessels, the temperature of the surface is maintained as body temperature. So what I am saying, that iris has blood vessels and blood flows continuously through these vessels. And because of blood flow, the temperature of iris surface is maintained as body temperature. So let us say it to be around 37 degrees centigrade. So the temperature of this iris surface is same as body temperature because it has blood vessels, and that is why the temperature of the surface, let us say that this is Th equal to 37 degree centigrade. Okay? Whereas this cornea is avascular tissue, this cornea which is bulged out part, that is avascular tissue, and avascular tissue means that it does not have any blood vessel. So, this cornea does not have blood vessels, and because of that the temperature of this surface will not be at body temperature, this corneal surface, because there is no blood. So, there is no blood flow through that. So, the another thing is, over this cornea there is a thin film of tears which comes out when we cry, and these tear films are continuously evaporating because we are blinking our eye continuously, and where there is evaporation there is cooling. So, because of that the temperature of this corneal surface is somewhat less than the body temperature, and let us say that the temperature is less than the body temperature, and we call it to be Tc equal to, let us say, 33 degree centigrade. So, what I am saying that the temperature of corneal surface is less than the temperature of the iris surface, and that happens because of blinking of the eye and the evaporation of tear film, and where there will be evaporation there will be heat transfer, and that is why the temperature at the surface will be less than the body temperature. Okay? So, you can see that clearly there is a gradient in temperature between this surface and this surface, and this temperature gradient drives the flow inside the anterior chamber. Yeah, so it is visible from that side. So, what happens here, the temperature of this bottom surface is higher than the temperature of the top surface. So, the aqueous humour which is near the bottom of this anterior chamber, that will have density lesser than density of aqueous humour which are there in the top, because density is completely dependent on temperature, and if there is higher temperature the density will be less. So, the aqueous humour here will have less density, and that is why the aqueous humour here will be lighter than the aqueous humour here. So, what I want to write here is this aqueous humour near the bottom iris surface is lighter than the aqueous humour which are there near the top surface, and that is because of difference in temperature. So, now this configuration is heavy over the light. So, the heavy fluid will try to come down and the light fluid will go up. So, because of that there will be circulation inside. Okay? So, what I am saying that this heavy fluid, suppose here we have a heavy fluid, below that there is a lighter fluid. So, the heavy fluid will come down because of gravity, because gravity is there in the vertically downward direction, and the lighter fluid will go up because of mass balance. If something is coming down, the other person will have to go, other fluid will have to go up. So, because of that the circulation will be generated inside the anterior chamber. So, the driving force for this circulation is temperature gradient inside and gravity. So, that effect, combined effect, is called as buoyancy. So, buoyancy is the driving force for circulation inside anterior chamber of eye. So, dimension is clear, driving force is clear. So, now we will write the governing equations. If you have any doubt you can ask. Yes. Yeah, there will be slightly mean temperature there, because here you are right, because at this surface and this surface the temperature are Th and Tc. So, there will be mean temperature, we cannot say about what is there, but we will say that let us take it to be Th there. Okay, if you have any other question you can ask. So, what we will do now, we will write the governing equations, because we are clear about what is the problem and what are the dominant forces which drives the flow, and we will solve for the velocity and pressure inside the interior chamber. Okay. So, now what I am going to do here, because we are solving this problem in Cartesian coordinate system, we have seen the governing equations, dimensional governing equations many times. So, I will not write the governing equations here in the dimensional form, rather we will choose the characteristics scale and we will try to make it dimensional. So, that time all the equations will come out. So, I am not writing the equations separately, where I am directly writing the characteristics scale and we will try to make the equations dimensionless. The other thing is, which I want to mention, that this iris and corneal surface are solid walls. Okay. So, they are solid walls. So, we will apply no slip and no penetration condition for velocity. Temperature we already saw that at the lower bottom surface, which is iris, and that surface is maintained at constant temperature Th, whereas because of blood flow, whereas the corneal surface, that is maintained at temperature Tc, that is also constant temperature. So, those are the two conditions for temperature. For velocity, we will take these walls to be solid walls, so that we can apply no slip and no penetration condition at both the walls. So, let me choose the characteristics scale for making the equations dimensionless. So, you can see that in the x direction, the characteristics dimension is length of the width of the anterior chamber. So, that is L. So, we can choose that L directly for the characteristics scale. So, we are choosing xc as L. Okay. Whereas, in the z direction, we have the dimension as depth of the anterior chamber. So, we will choose the characteristics scale as zc equal to b. And yeah, z equal to b. So, now we need to choose characteristics scale for velocity. So, we are choosing uc, which is characteristics scale for velocity in x direction. So, that I am choosing as nu upon L. So, nu is kinematic viscosity that have unit meter square per second, because we do not have any obvious characteristics scale for velocity, right. So, we will choose that to be nu upon L, which is meter square per second upon meter, will be meter per second, and Wc, which is characteristics scale for velocity in z direction, we will calculate it from continuity equation. And yeah, let me not write it here, I will calculate, I can write it also here, but I want to show you that what it will come. We have done that all earlier in the class also. Now, let us choose the characteristics time scale. So, that is Tc, that will be nothing but, so let me call it to be capital U, because every time I do not want to write nu upon L. So, I will write that to be capital U. So, characteristics time scale will be L upon U. So, meter upon meter per second, that will be second. Okay. The another thing which will come out in the problem is temperature, because that is also dependent variable. So, I am choosing the characteristics temperature as dimensionless temperature as T minus Tc upon Th minus Tc. Why I am choosing like this is, our main objective for making equation dimensionless is, we want our dimensionless dependent variable to vary between 0 to 1, and that is what you will go and see in your notes, that whenever we have tried to make the equations dimensionless, we always want our dimensionless variable to vary between 0 to 1. So, if you will check T star, that what is the limits, upper and lower limits of T S star, you can see that when we will put this T S T C it will be 0, and when we will put this T S T H it will be 1. So, this T S star is varying between 0 to 1, that is why we are choosing the dimensionless temperature in this form. So, what I will do now, I will write the governing equations. First let me write as continuity equation, equation of continuity. Let me write EOC, equation of continuity. So, what is it? In Cartesian coordinate it is dou u upon dou x plus dou w upon dou z is equal to 0. So, this is dimensional equation of continuity. We want to make it dimensionless. So, what we will do, we will put u equal to u star into u, this u. So, it will u will come out, and for x this is L. So, this will be dou u star upon dou x star. You have done non-dimensionalization many times in the course. So, that is why I am doing it directly, and for w let us say that WC is the characteristics scale, and for Z we have already seen that it is B, and this will be dou W star upon dou Z star, this is equal to 0. Yes. That is not V, that is nu. So, nu is mu upon rho, kinematic viscosity. So, this is nothing but mu upon rho. Y direction? Oh, okay. So, what I am saying that the things are axisymmetric about y. So, that is why I will not, like you have chosen, when you, this is 2-dimensional problem. So, in one direction we are saying that the I is axisymmetric in y direction. So, that is why we will solve for x and z only, because this dou u star upon dou x star and dou w star upon dou z star are order of 1, because these are dimensionless quantities. So, this u upon L will be, should be equal to WC upon B, and from here WC will be equal to B times B upon L times U. Okay? And as B is the depth of the anterior chamber, L is the length of the anterior chamber, and I said that the ratio of these two quantities will be very small. So, I am representing that B upon L ratio as epsilon. So, this WC will be epsilon times U. So, what I am saying here that epsilon is another quantity which is ratio of depth of the anterior chamber upon width of the anterior chamber, and this will be less than 1. So, this is a small quantity and this is epsilon. So, here if you will see, this WC will come as epsilon times U, we saw it earlier, and if we want to replace this B, so then B will be equal to epsilon times L from here. So, I will write B as epsilon times L. Okay? So, this is our equation of continuity. Now, we will do for the x momentum balance. So, our equation of continuity in the dimensionless form will be dou u star upon dou x star plus dou w star upon dou z star, this is equal to 0. This is our dimensionless equation of continuity. Okay? And one thing from here, I want to erase this part because I will start with the x momentum balance. So, what I will do here, I will write T equal to here. So, T will be equal to T c plus T h minus T c into T star. I think I will not be able to use that today, but that is the expression for T. Now, I will erase this part. Let me complete the x momentum balance. So, we are doing for the slipping position of I, and now we will do for the x momentum. So, x momentum balance is rho naught times dou u upon dou t plus u dou u upon dou x plus w dou u upon dou z is equal to minus dou p upon dou x, I will erase this also, plus mu times dou square u upon dou x square plus dou square u upon dou z square plus rho times g x. So, gravity is acting in the z direction. So, this g x will be 0 because that is vertically down. So, the normal component of that will be 0. So, this is our x momentum balance. Now, let us make it dimensionless. So, u is there present in all these terms. So, I will take u c as common. So, that is capital U rho naught times u, and this will be that for t it will come as L upon u. So, u upon L dou u star upon dou t star plus here it will come u upon L u star dou u star upon dou x star plus epsilon u upon, for z it will come as epsilon L because that is b is equal to epsilon L w star dou u star upon dou z star, that is equal to minus, for let us say that the characteristics scale for pressure is unknown and that is P c. So, P c for x it will come as L, it will be dou P star upon dou x star plus for u this again it will be u c which is capital U, and this will be, I will write here mu times u, and okay, let me write it down here. So, this is mu times u and it will be 1 upon L square dou square u star upon dou x star square plus 1 upon epsilon square L square dou square u star upon dou z star square, right. So, what I did for x the characteristics scale is L. So, it will be L square, for z it is epsilon L. So, it is epsilon square L square. Now, I will take epsilon square L square common from this viscous term, viscous force term. So, this will become mu upon epsilon square L square, and because I am taking epsilon square L square common. So, this will become epsilon square and this will become 1. So, this is our x momentum balance in dimensionless form. What I will do, I want to simplify it slightly more. So, I will divide both the sides with this mu u upon epsilon square L square. So, this will become, from here this u by L is again common from all the terms because this epsilon will cancel out. So, that will be rho naught times u square upon L, and that term the whole LHS term I am writing as Lagrangian derivative. So, dou u star upon d u star upon d t star, this is equal to minus P c by L into, I am multiplying everything by epsilon square L square upon mu u. So, epsilon square L square upon mu u, let me erase this also, mu epsilon square L square upon mu u times dou p by dou x plus epsilon square dou square u star upon, so this is a star, this is a star, by dou x star square plus dou square u star upon dou z star square. Okay. Oh, here also we need to multiply, yeah. it will come directly. If you will do so, I won't do it directly, that is what I wanted to do in the next step. So, this will be rho naught u square upon L into, I am multiplying by epsilon square L square by mu u. So, this L and L will cancel out. So, this if you will do, this will come as epsilon square R e. Yeah, one person got it also. So, this is multiplied by du star upon dt star, and where R e is nothing but rho naught u L upon mu. So, here it will become L will again cancel out. So, it is minus P c upon mu times u upon epsilon square L into dou p star upon dou x star plus epsilon square dou square u star upon dou x star square plus dou square u star upon dou z star square. So, now again we will equate the coefficient of this pressure gradient to 1, and from here we will get P c as mu u upon epsilon square L. Okay. So, if P c is this term will become 1. So, this is our x momentum balance in dimensionless form. Now, again this epsilon square is very small quantity, yeah, minus will be there. So, again this epsilon square is very small quantity. So, this term will have very small magnitude. So, we will set it to be 0 because epsilon square is small, and again if you will calculate R e, because the properties of aqueous humour is similar as water. So, we will calculate R e by putting the physical properties of water. This epsilon square R e will also come out to be small. So, again this LHS term will, all LHS term will be equal to 0. So, that is not equal to 0, that is very small. So, this and this term will not contribute at the leading order. So, we will have simplified dimensionless x momentum balance as minus dou p star upon dou x star plus dou square u star upon dou z star square, that is equal to 0. So, this is our dimensionless x momentum balance. We will start with z momentum balance and energy balance equation tomorrow, and we will see how this u z u w and pressure will look like, and then we will draw also the streamline of this aqueous humour inside the anterior chamber. Okay? Thank you.